So let's continue our discussion of electric potential, talking about the electric potential around the simplest of objects, just a simple point charge. So here we have a point charge Q. So Q could be positive Q or negative Q, any value. It doesn't necessarily have to be a positive charge, it's just some value. And we want to know what the potential is at point P, distance r away from that point charge. So P could be anywhere. I could draw P anywhere, any distance from Q. I'm going to be able to say, what is the potential at that point? Well, we already did this with the electric field. Right? So the electric field was equal to the electrostatic constant K, which again is 8.99 times 10 to the 9th newtons times meter squared over coulomb squared. Like constants given in your book. Whatever the value is of the charge Q, divided by the distance from Q squared. So if I know what r is, if it's a meter or centimeter or millimeter or whatever, I square that distance. Q is the magnitude of the point charge, and K again is just a constant. Remember that the electric field, which should have units of newtons per coulomb or volts per meter, either one is valid. The electric field is a vector, so it will have some magnitude and direction at this point. For example, if this is a positive charge Q, it gives me a positive electric field at that point. If I place another positive charge here, they're going to repel one another, like charges repel. So the electric field will point away from charge Q. If this is a positive charge and this is negative, or this is positive and the main charge is negative, either or, the electric field will point towards Q because they attract one another, unlike charges attract. The potential is different. The potential is a scalar. There's no direction associated with it. The potential actually looks a lot like the electric field equation. It depends on constant K. It depends on charge Q, but it's only divided by r to the first power, not r squared. So the potential is K times Q over r. If Q is positive, the potential is positive. If Q is negative, the potential is negative. And of course, you can see how the potential drops the further you get. As r gets bigger, right? So this gets further and further and further away. R gets bigger, the potential gets smaller. So one analogy that I like to use is to think of the electric potential a bit like an elevation map. If you've ever seen a topological map, right, of a mountain range or your city or the Wausau area, for instance, for those of you who live in central Wisconsin, although if you're getting this online, chances are you're probably all over the state or nation. If you have a nearby hill, a large hill for skiing or just sightseeing, and the topological map, you'll see the elevation markers get higher at that location. That gives you an idea of how high above sea level you are, of course. That's the idea of these maps. Potential, electric potential, you can think of it the same way. The bigger this electric potential, the closer you are to this charge. So imagine that this whiteboard is made of, say, a flexible material like rubber. A positive charge, I would actually pull in 3 dimensions, pull this charge out, creating a mountainous peak coming at the camera that would fall off the further you get from the camera. So a positive charge you could think of as wanting to roll downhill. Now this analogy doesn't work very well when you talk about negative charges because negative charges want to roll uphill, which of course there's no gravity equivalent for that. If this charge is negative, it's as if I'm pushing the flexible material in, creating a valley or a hole where positive charges want to flow down into the hole towards the negative charge. So potentials, again, the best analogy I can think of is to look at it in terms of like an elevation map. So for elevation maps, of course, if you have a big boulder or a bowling balls roll from high potential to low potential. That's naturally how they roll, from high gravitational potential energy to low gravitational potential energy. Likewise, positive charges act like bowling balls in that analogy. They go from hot areas of high potential to areas of low potential. They want to roll downhill. Again, the caveat is that negative charges do the opposite. Negative charges move from low potential to high potential. Think of them as wanting to roll uphill. The gravity analogy breaks down because gravity only works in one direction, whereas the electrostatic force works in two, right? It's a push and a pull, whereas gravity is only a pull. So if I know what the charge is of a point charge, I know how far away I am from that point charge, I can tell you what the potential is at that point. It doesn't give you any information regarding where that bowling ball is going to want to move in my gravity analogy, or where, if I drop a positive charge there, what happens, right? This just tells you an elevation. It's like if I told you, oh, I have a bowling ball at 1,000 meters. It's like, well, I need to know what's around it in order to tell you what the bowling ball is going to do, right? Is 1,000 meters the bottom of a hill? Then the bowling ball is going to sit there. Is 1,000 meters the top of a sharp mountain? Then the bowling ball is going to want to roll downhill. Just telling you it's 1,000 meters isn't enough information. You have to figure out what the potentials are around the area to see what direction the charge is going to want to go. So in that case, the electric field is more valuable in this location because it will tell you what direction the particle is going to experience a force. But if you know the potential difference between 2 points, point A has a potential of 12 volts, point B has a potential of 6 volts. You know that positive charge is going to want to go from 12 volts to 6 volts. It's going to want to roll downhill, right, from high potential to low potential. Now, these two equations we've talked about before, but I'm just putting them up there as an analogy. The electric field is related to the electrostatic force. You just multiply test charge Q. So instead of at point P here, I drop a little charge Q at that location. That doesn't look very good. Let me redo it. So at that point P, I drop charge Q. I can now tell you what the force is on that particle because I know what the electric field is using this equation. So I can tell you what the value of the force is. And I can tell you what the electrostatic potential energy is of the system because I have charge Q now, and I have the potential, which just depends on the point charge, big Q, and the distance between these two charges, R. So again, see how similar these equations are, but they are distinct. The electric field goes as 1 over R squared. The electric potential goes as 1 over R.